Hi, my name is Ethan Dreyfus, and I'm from Stanford University. This summer I worked on improving our software to help the robot recognize and interact with people. The cool thing about personal robotics is that it brings robots into the same environment as people. This means that the robot can, and in fact must, interact with people. One of the simplest sorts of interactions possible is to directly command the robot, for instance, by driving it forward with a joystick. Very quickly, however, you'll run into situations where you need more sophisticated interaction from the robot. For example, suppose you're carrying something. Then you may well want to direct the robot, but trying to manipulate a joystick is no longer possible. What you need is more intelligence from the robot. You want it to be able to recognize you as a person and follow you around without any work on your part. The person-following problem has a number of challenges, among which are that people are highly varied in appearance and pose, that real environments are highly cluttered and poorly lit, and that the robot is not the same size as a person and cannot blindly follow the same path that a person takes. The problem can be broken down into two different parts: tracking a person and navigating to stay close to the person. I focused primarily on the tracking task and used a slightly modified version of our navigation stack to keep the robot close to the person. Our tracking takes a multimodal approach, fusing together multiple independent detections of people or parts of people, which each have their own strengths and weaknesses. The current system uses three different detectors: a face detector, a height-based tracker, and a leg detector. The face detector is a standard Viola-Jones system, and is highly accurate when the person is close to the robot and facing it, but fails completely if the person is not facing the robot. The height-based tracker uses stereo vision to track the motion of objects approximately the size and height of a person. Its key advantages are that it can almost always see the top part of a person, which is all that it needs. Its main disadvantage is that it can easily become confused when several people are nearby. The leg detector searches for objects which look like legs in the base laser scanner. Since the laser is highly accurate, this detector is quite robust to people in close proximity to one another. However, it can become confused by objects such as chair and table legs, and is vulnerable to objects coming between the robot and the person. To get the best of all possible worlds, we fused these detections together with a particle filter which could easily be extended to handle additional detectors. My other major project this summer was the collection and annotation of a large data set of people in an indoor environment. Much of the existing work in the field of person detection and tracking has revolved around outdoor pedestrians. We hope to encourage the community to tackle the challenges of recognizing and tracking people in an indoor environment by making a high-quality data set available. All of the software I wrote is freely available and can be found in the People package at ross.org.